Hi everyone. Thanks. I would like to thank the organizers for putting together such a great conference and inviting me to speak to you today about my project with Nicolas Delfos. And the project is about how to use toric-code decoders to decode the color code. So I'll present sort of a plug-and-play construction. So let's get started. We want to do some quantum computing, and we know that there would be always some noise when we run our quantum computer. So we need to use quantum error correcting codes to reliably store and process quantum information. And in my talk, I will focus on a special type of quantum error correcting codes, topological codes. You should think of those codes in a geometric way. You have some manifold, say a torus, and you would place physical qubits on the side of the torus. And a topological code will have a geometrically local generators. So your operators are supported only within some local region. However, the logical information is encoded non-locally in the system. So in particular, if you were to apply a logical Pauli operator, for instance, it necessarily has support which forms, say, a non-constructible loop. So those codes are particularly well, they perform particularly well if your noise is local, because your logical information is encoded non-locally. And two examples of topological codes, which we will see in this talk, and which you probably know well, include the toric code and the color code. Why do we think about topological codes? Well, those codes exhibit many desired properties. And first of all, they can be built in the lab. You can have a two-dimensional architecture. You can build those systems, and there are many groups trying to build small patches of the surface code. Also, topological codes have many fault-tolerant logical gates. Those codes, we know how to decode them efficiently, and generically those codes exhibit high thresholds. And in the talk, I will focus on those two properties of topological codes. So to this community, I don't need to motivate or explain the decoding problem, but I will very briefly go through this slide. So in my talk, I will be limiting the discussion to stabilizer codes, which are defined by a set of commuting Pauli operators. And the code space is the +1 eigenspace of all the stabilizers. So the game we will be playing, the quantum error correction game, is the following. We have some information. We encode that information in a stabilizer code. And then there is some noise which can corrupt our code word. So our information is encoded. We have some code word. But if there is some noise applied to it, this information, this state will be moved outside the code space. So then what we will do is we'll measure some stabilizers, and this will discretize the errors, and it will allow us to diagnose what errors affected our system. So when I say the decoding or a decoder, I mean this part of this quantum error correction game. So decoding is a classical algorithm which allows us to find error correction from the observed classical syndrome. And of course, we win this game if the information we put in is the same as the information we read off at the end. In the talk, I will spend quite some time talking about thresholds. So what's a threshold? We can think of the threshold as the maximal error rate the code can tolerate. And the threshold depends on the code family we analyze, on the decoder we use, and also on the noise model, which affects our system. So we've heard that one of the leading approaches to scalable quantum computing is the 2D toric surface code approach. Unfortunately, there's a difficulty with this approach, namely, we don't quite know how to implement a fault-tolerant non-Clifford gate. And such a gate is needed for universality. If we were to have a fully functional useful quantum computer, we need a non-Clifford gate. So that's where the color code comes into play. The color code can be viewed as an alternative to the toric code approach. So first of all, when we consider, say, the triangular color code, it can be more qubit efficient than the rotated surface code to get the same distance. But that's not all what the color code is about. Color code is very interesting because it has many transversal logical gates. In particular, in the d-dimensional color code, one can access div level of the Clifford hierarchy. What it means, for instance, for the 2D color code, we can get the Clifford group, the logical Clifford group. Those transversal logical gates allow one to avoid state distillation. So in particular, with the color code and its three-dimensional version, we can circumvent magic state distillation by doing some code switching and getting the non-Clifford gate via transversal gate. And lastly, there has been a proposal called Colorful Quantum Computing from the last fall by Hector Bombin, and this really relies and exploits all the good properties of the color code. Unfortunately, there seem to be issues with the color code. This is not the end of the story. The color code is not the solution to all our problems. So, namely, the color code seems difficult to decode, as we will see, and also it seems to exhibit worse performance than the toric code. So, after this short motivation, let me tell you what the main result is, which I will present and sketch the outline of the talk. So, in the talk, what I will describe to you is a class of efficient decoders for the color code in any dimensions, and those decoders will exhibit high thresholds. So I will very briefly describe to you the toric code and the color code in 2 dimensions. And I will stay in 2 dimensions, and in 2 dimensions with many pictures, I'll try to explain to you what the restriction decoder is. And you should think of this decoder as a plug-and-play decoder. Having a toric code decoder, we will be able to decode the color code. Then I will show you some numerics, and we will see that the color code performance matches the toric code performance. Then I will switch gears and show you some technical details, and in particular, I will sketch how one can go to higher dimensions, beyond 2 dimensions. And the last part will be a little digression. I will tell you a bit about neural network decoding. So let's get started. So we all know and love the toric code. So what's the toric code? We take the square lattice. It doesn't have to be the square lattice, but let's consider the square lattice for simplicity. With periodic boundary conditions, we will place qubits on edges, and then the code is defined by its z and x stabilizers. For every face, we will have a z operator, and for every vertex, we will have some x operator. This is a CSS code. The z and x type stabilizers don't mix with one another. So we can consider in the problem of decoding, we can consider x errors and z errors separately. So let's focus on z errors. So let's assume that some qubits are affected by z errors. Those qubits are depicted in light blue. So what do we do to find out that there are some errors in the system? We measure x-type operators. So some of them will be unsatisfied, will be violated. In particular, those 2 x-type vertex operators will be violated. And I will refer to those violated stabilized generators as excitations. And what we need to keep in mind is what we can see is that those excitations are always created in pairs, as we can see in the picture. So what does decoding boil down to? It's really finding a position of errors from violated stabilizers. So we know those 2. We know those 2 crosses, and now we want to make a guess what error happened in the system. And the problem of decoding basically boils down to pairing up excitations. So if this is my initial error, and this is my guess, the dark blue, I say that the decoding succeeded because the error and the correction differ by a stabilizer. We can see that the error and the correction form a stabilizer. However, if my guess is forms a non-contractible loop, it causes a logical operator and the decoding fails. So there have been, this is quite an old problem, and there have been many decoders for the toric code, and by no means this list is an exhaustive list. I just wanted to give you a flavor what techniques can be used to decode the toric code. People use decoders based on the minimum weight perfect matching algorithm. One can use certain cellular automata to decode the color code. One can use some ideas from a normalization group approach or from tensor networks. Okay, so now let's switch gears and talk about the color code. The color code can be defined on a lattice in 2 dimensions. However, this time we require that the lattice satisfies 2 properties. So the lattice has to be composed of triangles, as we can see here, and the vertices of that lattice have to be 3 colorable, meaning 2 vertices incident to the same edge have to be colored in 2 different colors, and there are 3 available colors. So the color code can be defined by placing qubits on triangles. Every triangle of the lattice will host 1 qubit, and for every vertex of the lattice, we will assign an X operator and a Z operator. And those stabilized generators will be supported on all triangles neighboring a given vertex. So this model is closely related to the toric code, and it also, this relation carries over in higher dimensions. However, decoding of the color code seems to be more challenging. And what's the origin of this seemingly difficult thing? So in the toric code, as I was saying, we can create excitations only in pairs, and the decoding boils down to pairing up points. However, in the color code case, we can create excitations in pairs, but also in triples. So let's see. So if there is some Z error in the system, depicted by 2 shaded triangles, there will be 2 violated stabilizers, those 2 green vertices. So we can think of this error operator creating a pair of excitations in the system. However, another Z-type error depicted here, this guy can create, and it does create 3 excitations, red, green, and blue. So indeed, a process which creates a triple of excitations is allowed. So in our decoding scheme, we don't only pair up excitations, we need to account for excitations being created in triples. So what's the setup? What's the problem we want to solve? This is our information. We have access to the syndrome, which is some subset of vertices. It's a 0-dimensional information, 0-dimensional object. And we want to make a guess about the error, which is a 2-dimensional object. It's some subset of faces affected by the error. So how do we do that? So before I tell you the answer to that, which carries over to higher dimensions, I need to introduce 2 notions. So the first notion is the notion of a restricted lattice, and the other one is a notion of a restricted syndrome. So let's assume that this is my color code I want to decode. The shaded triangles are the errors, and highlighted vertices are the syndrome I measured. So a restricted lattice of color red and green is obtained from the initial lattice by keeping all the vertices of color red and green and edges connecting those vertices. So that would be the restricted lattice. Similarly, the restricted syndrome, RG, would be to keep excitations of color red or green. So that's pretty straightforward. So what is the restriction decoder now? So as I said in the previous slide, we start with a 0-dimensional syndrome, and we want to get an estimate of the error, which is 2-dimensional. So the first step of the restriction decoder would be to view some part of the color code syndrome as the toric code syndrome, and use the toric code decoder to get some object which will be 1-dimensional. So starting from points, we will get some edges. And then this object will be used later in some local lifting procedure to get an estimate of the two-dimensional error. So how does this work in detail? Let's see that in an example. So the first step is we will consider the restricted lattice, red-green, and the restricted syndrome. And we will use the toric-code decoder to find the appropriate pairing of those excitations. So I will call it the blue pairing. So we just pair up excitations in that lattice. And we will do it also for the other restricted lattice, red-blue lattice. And I will call this pairing green. Then the next step is to combine those two pairings. That's what it's going to look like. Remember, I don't know the shaded triangles. The shaded triangles are just, they just depict where the error is, but we don't have access to this information. So the second step of the information is to use the local lift. So what does this do? The local lift does the following. For any red vertex, the local lift finds some subset of neighboring faces of that vertex whose boundary locally matches the blue and green pairings from the previous step. So let's see that in action. So for this red vertex, I pick those triangles shaded in pink, and you can see that the boundary of those triangles locally matches the green pairing. Then I proceed with another red vertex, for instance this one, and I can pick this triangle, and the boundary of this triangle locally matches the green-blue pairing. And I do it for every single red vertex of the lattice. And the output of the restriction decoder is basically the union of all the faces picked in the second step. So now I'd like to make a couple of comments on the restriction decoder. So I would like to emphasize that any toric-code decoder can be used as a subroutine in the restriction decoder. Also, the restriction decoder threshold is determined by the toric-code threshold. Also, I would like to contrast the restriction decoder with a previously considered decoder, the strategy called decoding by projection. The restriction decoder can be viewed as an improvement and a simplification of the decoding by projection. So first, the restriction decoder never aborts. It always gives a valid correction for the color code. Moreover, the restriction decoder uses two restricted lattices. Also, the lifting procedure in the restriction decoder is local. And lastly, the restriction decoder can be straightforwardly generalized to higher dimensions, unlike the method of decoding by projection. So one can consider many modifications of this idea, because I would like to emphasize that the restriction decoder is sort of a pretty generic framework how to decode a color code. We use some toric-code decoder and a lift procedure. So we can play a bit with the components, and for instance, one can have a version of this decoder which does not require any restricted lattices. So what we can do is we can just consider red and green syndrome and pair it up within the original lattice, and do the same with red and blue syndrome. But then the lift procedure has to be applied not only to red vertices but also to green vertices belonging to the blue pairing, and green vertices and the blue vertices belonging to the green pairing. Also, it's kind of interesting to see how those ideas can be used, for instance, to analyze fractal models or quantum pin codes. We will hear about them from Christoph tomorrow. So now I'd like to show you some numerics. So what we considered was the 488 lattice with the periodic boundary conditions. We considered the phase flip noise and ideal measurements. And what we saw is that the color code threshold is 10.2%, and that value is very close to the toric code threshold with the minimum weight perfect matching decoder, which is 10.3%, around 10.3%. And I would like to emphasize that previous highest thresholds for the color code were in the range of 8.7% So this is quite a substantial improvement for the code capacity case. And we also implemented a decoder for the color code, which runs in almost linear time. So this can be achieved by replacing the minimum weight perfect matching decoder as a subroutine. We use the union find decoder. And we see that the performance of this very fast decoder is fairly close to the one using minimum weight perfect matching. The threshold shifts slightly. However, we can access lattices much bigger. Okay, so now I would like to tell you a bit about how to go beyond 2 dimensions. So in order to do that, let me introduce very briefly a notion of a CSS chain complex. So we heard about CSS chain complexes earlier in the talk by Leonid. So what is a CSS chain complex? It's a sequence of F2 linear vector spaces and linear maps between them. So elements of that vector space correspond to qubits. Elements of this vector space correspond to z-stabilizers, and elements of that vector space correspond to syndrome configurations we can observe. And what do those boundary maps do? And this boundary map takes a stabilizer and returns its support, and that boundary map takes some z-type error and returns its X syndrome. So this may be a bit abstract. Luckily, there's a very nice interpretation of the CSS chain complex for topological codes, and from now on we'll work only with pictures. So what is it? So when we have a topological code, there's an underlying lattice on which the code is defined. So in case of the toric-code, the chain complex will have this form. So to see an example, let's consider the toric-code in 2 dimensions. Those vector spaces will correspond to faces, edges, and vertices. Or in other words, z-type stabilizers will be identified with faces, qubits will be placed on edges, and x-type syndrome will be identified with vertices. The chain complex doesn't have to look like that. It doesn't have to be k plus 1 dimensional cells, k dimensional cells, and k minus 1 dimensional cells. It can be more complicated, as is the case of the color code. So for instance, for the 3-dimensional color code, z-stabilizers can be identified with the vertices of the lattice, qubits will be placed on a tetrahedra, and X syndromes will be identified with some subsets of edges of the lattice. So we see that the dimensionality of the cells in this chain complex changes. It's not only decreasing by 1, it's kind of changing in some way. And this number k tells you how it changes. Okay, so with that, I can tell you how to go beyond 2 dimensions. So the restriction decoder for the 2-dimensional color code on some lattice L is, as we saw in 2 dimensions, it consists of some toric-code decoder, which will be working within the restricted lattice of certain color. And the second component of the restriction decoder is a local lifting procedure. And when we are in higher dimensions, there's some, one has to be a bit careful how this restricted lattice is defined, and but I don't want to go into the details how this restricted lattice is defined. Just a word of warning, in the restricted lattice in higher dimensions, we need to add certain cells, and we need to make sure that the topology of the restricted lattice matches the topology of the original lattice. And this is captured by our first theorem in the paper. So what we prove is that the Cave homology group of the color code lattice L is isomorphic to the Cave homology group of the restricted lattice. We also show the following lemma. We establish a morphism between the color code and the toric-code chain complexes. So you may remember that the top sequence of vector spaces captures the color code into dimensions. The bottom sequence of vector spaces captures the toric-code dimension. Those pies are some linear maps, and those linear maps establish a morphism between the color and toric-code chain complexes, or in other words, the structure of the decoding problem is preserved by this those linear operators. And this leads us to the final theorem of our paper, which is that the restriction decoder for the d-dimensional color code succeeds if and only if the toric-code decoding on those restricted lattices succeeds. So now I would like to show you more numerics and make some comments. So in higher dimensions, we consider the three-dimensional color code. We pick the BCC lattice, which can be viewed as two cubic lattices, two interleaved cubic lattices, and this lattice is filled with tetrahedra. We consider the phase and bit flip noise and ideal measurements. And in 3 dimensions, there would be 2 types of excitations. There would be 0-dimensional point-like excitations, and unlike in 2 dimensions, we will also have another type of excitations which form one-dimensional objects, one-dimensional loop-like objects. So the numbers we got for the restriction decoder for this setting are the following. For 0-dimensional excitations with the minimum weight perfect matching decoder, we got a threshold of around 0.8%. For the 1D type excitations with the sweep decoder, we got the threshold of around 13%. So what do those numbers mean? They should be contrasted with the optimal thresholds, which can be obtained using some statistical mechanical reasoning, as Chris was telling us yesterday. And for the color code in 3 dimensions, the corresponding numbers would be 1.9% and 27.6%. So we see that in 3 dimensions, the decoder performs okay, but there is still room for improvement. And lastly, I would like to make a comment that when we consider the restriction decoder, which uses as the toric-code subroutine the sweep decoder, this procedure can be viewed as a cellular automaton. And the caveat is that this would work for color code in 3 or more dimensions, and when we have no point-like excitations. So since I still have some time, I would like to make a digression about neural network decoding. So there are some challenges in designing decoders. And in general, the problem of decoding an arbitrary stabilizer code is a computationally hard problem. Moreover, we may not quite know the dominant sources of errors in our system, or if we change the hardware architecture, those sources of errors may be vastly different. At the same time, the decoders we analyze and design, as the one I just talked about, they are usually designed for very simplistic noise models. For instance, for the bit flip noise model. But then a natural question would be, can we easily incorporate correlations between the errors? So for instance, if we have correlations between X and Z errors, or maybe some spatial correlations. But that's difficult to do that. Also, some codes may be quite similar, but their decoding strategies can be quite different. And I'd like to show you the following example. So imagine I have some layout of physical qubits, and now I choose to measure those stabilizers. This is the triangular color code in 2 dimensions. But I may have the same physical layout of qubits, but this time I will measure a different set of stabilizers. For instance, this one. And now I have the toric code with a twist. And the decoding problem of those 2 models a priori is not related. So how do I handle such a situation? So it would be very beneficial if we have some approach to decoding which minimizes our input, because our time is presumably quite pricey. Also, we would like to have decoding methods which would be easily adaptable to different noise model or different code. As we saw in this picture, you know, the physical layout of qubits is the same, but I just chose to measure different stabilizers. And lastly, we want to have an approach which will result with efficient decoders with good performance, good threshold. So when we think about that carefully, we can quickly realize that the decoding problem is very well suited for machine learning techniques. And my collaborators, Nishan Mascara and Thomas Joachim O'Connor, and I, we wanted, some time ago, we wanted to explore the adaptability of vanilla neural network decoding for various codes and correlated noise models. So as a test bed, we picked the triangular color code and the toric-code with a twist. And I would like to emphasize that in our explorations, we didn't put in any information about the geometric structure of the code or about the underlying noise model. And we didn't really want to tune neural networks. We just wanted to pick off-the-shelf, very simple method, and we wanted to check if such a neural network can handle different noise model, different codes. And what we saw is that neural network decoding is very versatile and outperforms leading decoders. So for instance, what I'm showing to you here is the results for the triangular color code and the polarizing noise model. We see that the projection decoder exhibits a threshold of 12.6%, whereas the neural network decoder provides a lot of improvement. It's 17.5%. But now you can still ask if those approaches are useful, because the codes we analyze are of small distance or relatively small distance, and this is for the ideal measurement settings. And there have been follow-up works, and indeed one can scale up the code distance, one can consider realistic circuit level noise model, and those decoders do seem to work. So with that, I arrived at the end of the talk. So in my talk, I presented to you the restriction decoder for the d-dimensional color code. You can view it as a plug-and-play decoder. It uses any toric-code decoder you want. And the second step of the decoder is the local lift procedure. We saw that the restriction decoder in 2 dimensions exhibits a very good performance, and in particular, it is better than all previous results for the 2-dimensional color code, and it is on par with a 2D toric-code minimum weight perfect matching decoder. Of course, there are a couple of questions to explore. One can ask about codes with boundaries, maybe more realistic noise model, the circuit level noise model, or one can ask if similar strategies work for other codes. And I guess a take-home message is that quantum computing based on 2D color code is worth pursuing. We shouldn't be fixated only on surface code. And with that, I would like to thank you for your attention.
Thanks very much. Are there any questions? Andrew.
That's a very nice talk, thank you. I would like to take issue, though, with this claim on your last slide that this 10.2% is better than all previous for the 2D color code. We know that optimally decoding the color code could be done with a threshold of 10.9%, give or take. Right. And even if you do the analog of the matching decoder for the color codes, finding the most likely error given the syndrome, work I did with collaborators years ago shows you can get 10.56%. So
But was that an efficient decoder?
they're not efficient, but it depends on what you're talking about. When you say
right.
better than all possible.
So okay, so I take your point. All or efficient decoders, yes, yes.
Hi, thanks. So I have two questions. So one is, have you compared, say, the color code versus the color code versus the toric code at some level below threshold, so like 1%, and then seen what the logical error rate is? So what does the error floor look like?
Oh no.
No. Okay. That's maybe more important than the threshold. And the other one was, I think I kind of missed what was going on with the projection decoder. So you said you compared this neural network decoder with a projection decoder that had some percentage that looked quite low for the polarizing noise model. So is this some decoder that isn't taking in, I guess it's the polarizing noise, so there's correlations between X and Y errors.
That's
so
right.
is the projection decoder taking into account those correlations, or is it something that's tailored?
It does not, because
that's why it's
we
bad.
would need to tweak it. We would need to adjust it.
Okay.
But on the top of my head, I don't know how to do it easily.
Okay, thanks.
There's another question over there.
So you presented the error model, which is just a channel model. Will it work in the fault tolerant regime?
So yes, so there is some ongoing work to benchmark that for the circuit level noise model for the 2D color code. So yes, you can incorporate the realistic noise model into that discussion.
I think there was one more question over here.
Thank you. It's a very nice talk. I wanted to ask if I've forgotten my question now. Yes, you said that the thresholds from the toric code carry over to the color code.
Right.
Is that from your numerics, or is that proven analytically?
So that's the result of our, we have a theorem. So the second theorem in our paper is that the restriction decoder succeeds if and only if the toric code decoding succeeds. So basically you have various copies of the toric code on different restricted lattices, and the toric code with the worst performance will determine the threshold of the color code.
Right.
So there's some function, and you can basically, it matches. But yeah, but this theorem establishes this fact.
I see. Thank you.
Right, we have one more question and then we can move on.
So this is a local mapping between the color code and some toric codes here. But in earlier mappings like this, even though it was local, like a weight 1 error in one model might go to a local but weight 2 error in the other model, so that optimal decoding in one setting doesn't translate to optimal decoding in the other. So does that hold here too? I mean, is there some concern that you might not be able to get the optimal results for decoding just through this local map to the toric codes?
That's right. So by no means you're guaranteed that it's optimal. What is good about this idea of considering restricted lattices is that if your initial noise model was uncorrelated, the noise model in the toric code on the restricted lattice is also uncorrelated.
Okay. If I may add an extra one here. So you talked about the, you said that you can use any decoder you'd like for the toric code to act as a proxy for the color code decoder. You talked about using the matching decoder. You talked about using neural net decoders. Have you considered looking at the tensor network decoder of Suchara, Bravi, and Vargo?
No.
That one should approximate the optimal decoder and get an even better performance, and you might find that translates to the color code setting as well.
Yes. Yes, so that would be definitely a good idea to explore, to take those tensor network decoders, and but with this procedure, with this framework of the restricted decoder, you can definitely do it. But we didn't check that.
Okay, thanks.
Okay, great. Let's thank Alex again.